Alright, so this is Griffiths Quantum Mechanics, problem 4.55. Probably one of the most enlightening problems in the book, I would think, is in terms of bringing all the different concepts together. Something which, I don't know, I don't think there's quite enough of in Griffiths' book, but this is a good problem. So, we have this, let's see. It's an electron in a hydrogen atom occupying the combined spin and position state of this right here. So the radial part, the angular parts, and also the spin right here. Okay, so we have 8 different parts to this problem, and we're going to start measuring different quantities. As far as the first 6 parts go anyway. So let's get started with what he wants us to do. So we have a part A. We are going to measure the orbital angular momentum squared. What values might we get, and what is the probability of each? Alright, well, we know that I'll draw an arrow like this. The measurements we would get for this are L times L plus 1 h bar squared. Okay, and so where do we find L? It's actually right here on the bottom of the spherical harmonics, right? There's L and there's M up there. All right, so L. And okay, here's a dumb mistake from me. This is a 0 and this is a 1. It wouldn't make sense to have L be a 0 and have a 1 for M. That would not be an allowed value. Okay, so there's the first mistake of the day. So what we have, the L of 1 and an L of 1. So it doesn't matter, there's no way of getting a measurement of anything besides L of 1 because that's the only spherical harmonics that we have in here. So L equals 1 with complete probability. So that gives us, so 1 plus 1 is 2 times 1 is still 2. So 2 h bar squared, and the probability is equal to 1, right? Which we could write as the square of this, so 1/3 plus the square of this, so 2/3. Okay, so on to part B. Same for the z component of orbital angular momentum, Lz. Okay, so what values do we get? We so the eigen values of this just M times h bar. All right, so what do we get? We have 2 different m's this time. So here's an m of 0 and here's an m of 1. So we get an answer of 0 with a probability, do a probability sub-0, I don't know, of, so here's the 0 and we're going to square this coefficient. So the probability is 1/3. Okay, and if we look at this one, we have an m of 1, so we get the z component of the angular momentum equal to 1 h bar, and the probability of that is going to be this coefficient squared, so 2/3. Okay. All right. So so we can see that these two will add up to 1 again, right? So total probability of 1. So that checks out. All right. Now let's look at the spins. So we have part C. now we're going to look for the spin angular momentum squared. All right. I forget what letters Griffiths uses. So I'm going to use S. I don't know. I forget what it uses. Okay, so it's exactly analogous to the total angular, or the orbital angular momentum squared. It's just we have the spin value here. So where do we find the spin? That's in the spinners. So this one has plus 1/2 h bar, and this one has a minus 1/2. Okay, so no. I made a mistake. This is, we're looking at the big S, or the spin angular momentum squared, right? So these are both 1/2, right? It's not till we look at the projection on the z-axis that we get the plus and the minus. All right, these are both 1/2 because it's an electron, right? So electrons carry a spin 1/2. Okay. So that gives us 1/2 plus 1 times 1/2 h bar squared. So what do we have? A 3/2 and a 3/4. Okay, and this is with probability equal to 1, right? Because the electron always has spin 1/2. All right. Okay. Part D. Okay, so now we're looking at the z component of the spin angular momentum. And like I said, I don't remember. I think he uses an m sub s for this, but then, anyway, whatever he uses, I should have looked. And multiplied by h bar. And this can either be a 1/2 or a minus 1/2, right? So now we're projecting the spin onto the z-axis. All right, so now we have a plus 1/2 here and a minus 1/2 here. Okay, so we are going to get, so for m equals 1/2, we get an h bar over 2, 1/2 times h bar. And that's with probability of this coefficient squared again, so 1/3. This kind of weird, awkward notation I'm using. I'll just put this subscript on here again. So, okay, the probability of h bar over 2 is 1/3. All right, but we can also get a minus 1/2 h bar. And probability of that, I'm just going to leave it as a minus. It's okay. Well, no, fine. Minus h bar over 2. All right, running out of paper, but we have, so here's the minus, and we're squaring this coefficient. So we get 2/3. Okay. Okay, so now we're on to part E. Okay, so for part E, it's going to get a little bit tricky. We're going to have to use the Clebsch-Gordon coefficients because we're going to start talking about the total angular momentum, and all we know right now is the orbital and the spin angular momentum separately. So we need to combine them using the Clebsch-Gordon coefficients to get the values for total angular momentum. So as far as the angular momentum goes, we have the spherical harmonics for our angular momentum, and these spinners for spin angular momentum. And so I'm going to write these in as kets, so it makes more sense with the Clebsch-Gordon coefficients as they're written in the book. So, what I'm going to do, and I hope this is not too difficult to follow, but we have these two parts, right? One with angular momentum, the L equals 1, M equals 0, and then a plus spinner, and then the other one is a 1, 1, and a minus spinner. So we have, I'm going to write these this way, and there's going to be lots of crazy colors flying around, so I hope I can keep everything straight. I'm going to use pink. I've already messed it up. Yeah, well, whatever. I haven't messed it up too bad yet. Alright, we'll just ignore the colors on this part. Like I said, already the colors have gotten tricky. Let's write these out this way. So we have here I'm going to write the angular momentum in red and the projection on the z in pink. Okay, so I hope this makes sense. And the reason why I'm doing this, I hope, will become clear later. All right, so here's the 1 and here's the 0. Let me just color this out if it helps. I don't know. All right, and then for this piece, we have a total spin angular momentum of 1/2, and for the plus, the projection is 1/2 onto the z. All right. Okay. Like I said, it looks weird now, but I hope it becomes clear later why we're doing it this way. It may not. Maybe this is all just a bunch of extra nonsense. Okay. Again, the pink is the projection part onto the z-axis, and okay, and then the red is the total angular momentum, or orbital momentum, spin momentum, orbital momentum, spin momentum. All right, because now, I hope the reason I'm doing this is because I made up this picture from the Clebsch-Gordon table. I only took a part of it, so, but this part you should be able to find, and then you just have to skip down like there's like one extra little section in between here, but skip down one and here you go. All right, so the reason I wrote that this way is because we're just gonna start with this state up here. So here's the 1 in red, the 1/2 in red, right? So the total orbital angular momentum, total spin angular momentum, and then the projections are down here. All right, so for this case, we have a 0 and a 1/2. We're looking at this bottom row right here. Okay, all right, so with that said, let's see if we can do our first, we're changing from an L and, all right, an M sub L. And an S M sub S. Okay, and we're going to re-express this in terms of J and M sub J. So the total angular momentum, orbital and spin together, and then that projection along the z-axis. All right, so I hope the colors will help. They may not be worth the time it takes to follow along, but whatever. Let's give this a shot. So our first one is we're going to do is this one right here. Okay, so we have a 1 and a 1/2 for our total orbital and spin momentum separately, and then we have a 0 right here and a plus 1/2 right here. Again, this is the plus spinner right here, and here's the ket we're using for our spherical harmonic, the angular momentum numbers here. Okay, all right. So here we go, Klebsch-Gordon. So like we say, here's our orbital and spin right here. We skip down to this row where we have 0 and 1/2, just like this. Now we're going to come over here and find our coefficients. Okay. So our first so when these coefficients are written, there's always a square root over them, and if there's a minus sign, it goes outside the square root. All right. So we have a square root of 2/3. Okay. Now we come up, so this is our first term. We're going to come up to here and look at our total angular momentum, 3/2 and 1/2. So we write 3/2 and 1/2. Okay, so good, so far so good. Now we have a plus sign, and now we'll go to our second term. Here's a minus 1/3. So this is actually a minus square root of 1/3, like this. And now we will go up to our numbers up here. So we have a 1/2 and a 1/2. Okay, so for total angular momentum, we get part of it, that's 1/2, and then with the z projection of 1/2 as well. All right, so here's our first one. All right, not too bad. Probably markers all over myself. Okay, now we find a clean piece of paper, and we're going to do our second one. So if we here's our second one, right here, right? So a 1/1 and a 1/2 minus 1/2. Okay, so I'll go ahead and write that out. We have a 1/1. Just double check, make sure. So 1/1, no, already. That's a 1/1, 1/2 minus 1/2. So this is a 1/2 here. Okay. And 1/1, 1/2 minus 1/2. All right. Okay. So this is going to be equal to, go to our table. Here's the 1/1, 1/2 minus 1/2. So this row, we come over here, we find our 1/3. So square root of 1/3 is our first coefficient, and that is 3/2 1/2. Switching between colors like crazy. Okay. 3/2 1/2, there's our first term. Okay, now we will add on our second one, which is going to be a square root of 2/3. Okay. And we come up here and we have a 1/2, 1/2. So total orbital angular momentum for this term is 1/2, and the projection onto Z is 1/2 as well. All right, let's set some markers down for a sec. And here's our two terms. So here's what we got before: the square root of 2/3, 3/2, 1/2. The minus square root of 1/3, 1/2, 1/2, and then these. So now we're going to add these together, and basically we're just going to combine terms so we get all of the terms in one place. But we do have to remember that there was a coefficient in front of each one of them in the beginning. So we have to include that. I'm going to just skip to using only purple for now, I think, just to save some time. So I hope that the colors helped with the Clebsch-Gordon coefficients. All right, so our new state, or newly expressed, right? We're just using a different way to express it. Right, we have this coefficient out here. Now we go to our first part here, the first term, which was this 1, 0, 1/2, 1/2. And now we have square root of 2/3 and the 3/2, 1/2. Okay. Minus a square root of 1/3, 1/2, 1/2. And there is our first part. Okay, now we're going to find our second part. So there's a coefficient out front, square root of 2/3. And then we need to find here's our 1, 1, 1/2, minus 1/2 state. So we're going to put that in here. So here we have a 1/3 under square root, 3/2, 1/2, plus a 2/3 under square root of 1/2, 1/2. Okay. Now we just have to combine these terms into, separate these all out by themselves, and we should be good. All right, back. So we'll go ahead and do this sum here. All right, so first what we need is, let's combine the terms with the 3/2, 1/2. So we have these multiplied together, so how do I write this? I'll just keep it under the square root. So we have a 1 times 2, which is 2, and 3 times 3, which is 9. Okay. All right, and then a plus 2. I wrote a 3. Wow, at least I got myself quickly here, more quickly this time. So this is a 9. A 2 times 1 is 2. A 3 times 3 is 9. I wrote a 3 again. Wow, it's early. Okay, 3 times 3 is 9. Okay, there's our coefficients for the 3/2, 1/2. Like this. Okay, now we'll do. We're running out of space, but now we're looking at this right here, which is just a 1/9 under the square root, obviously just a 1/3, right? But there is a minus sign out here. Okay, so minus sign from this. Now we have a plus 2/3, or 2 over square root of 9. Or I mean 4 over square root of 9. not consistent with the other ones, we'll fix it. All right, and this is the 1/2, 1/2. All right, now let's write this out more properly. So we have a 2 square roots of 2 from up above, and then we have just a 3 on the bottom. Is that right? So 3 on the bottom just factors out square root of 2 plus square root of 2. 2 square roots of 2. Okay. Okay. And then this is just 2/3 minus 1/3. 1/3. 1/2, 1/2. Like this. Okay, so here is our new way of representing our 2 angular momentum pieces in the total angular momentum representation. So again, what this is, these are the blue ones, right? So let's take one more moment and write them all out. And the same colors as before, just so we can compare back to, review back if that's what you want to do. All right, so these are the blue, all right, the total angular momentum. Okay, so with that said, now we can go on to part E, where we say if you measured big J squared, what values might you get, and what is the probability of each? Okay, well, we have 2 values we might get. So the first one would be a 3/2 multiplied by 3/2 plus 1 h bar squared. Okay, so this is for big J squared. Okay, 3/2 multiplied by 3/2 plus 1 h bar squared. So here we have a 5/2 inside here. So that's a 15/4 h bar squared. Probability, I won't write the cheesy subscripts this time. The probability of this is just this purple coefficient squared, which is, so we get a 4 times 2, so that's an 8. 3 on the bottom is a 9. So there's an 8 out of 9 chance that you're going to measure a total angular momentum of squared of 15/4 h bar squared. Square on the h bar. Okay? All right, so, and then what's the other one that we can get? Well, the other one is from this state, or this term over here. So we have a 1/2, 1/2 plus 1 h bar squared. So the other option to get when we measure the total angular momentum squared, big J squared. Okay, and so here's 3/2 inside here. And did I do that right? I think so. Yeah, so 3/2, 3/4. So 3/4 h bar squared. Okay, and the probability of this one is just this coefficient squared. So 1/3 squared is 1/9. And that's satisfying because 1/9 plus 8/9 is 1. So our probability sums to 1, so that's a good sign, right? Okay, so here's our, again, the values we can get when we measure big J squared are 15/4 h bar squared or 3/4 h bar squared with probability 8/9 and 1/9 respectively. All right, well, that was a workout. Now we have part F. which is what do we get for JZ? One of our 99 problems. We have again, we'll just look at this state. This time I'm going to use light blue because now we're looking at these numbers here. All right, so again, our eigenvalues are just mh bar. So we get a value. I'll just number these. Okay, so one of them is 1/2 h bar. Okay, and the other one is also 1/2 h bar. Well, that's the only option we have. We could sum up the squares of these coefficients again and get 1/9 and 8/9, sum them up again to 1. But since the only option we get for our the z component of our total angular momentum is 1/2 h bars, the probability of this is equal to 1. Okay, so part G, we go back to our original wave function here, because we're going to say, so if you measure the position of the particle, what is the probability density for finding it at r, theta, and phi? So the probability density, right, is the wave function squared. All right, so what this will give us is an R21 conjugate, an R21, right, and then we are going to multiply this by, we're just going to take the square of this part, the angular part. The spins won't concern us here because they don't have anything to do with our position. And so we have a 1/3 y10 star and a y10. All right, and then when because these spherical harmonics are orthogonal, we don't have any cross terms, right? So we won't worry about y10 and a y11. Right? We'll just use orthogonality to not worry about those. So the only other term we have is the square of this one. Little star there. All right, and so this part is all multiplied by this radial part. Okay. All right. So now it's somewhere around here. I wrote down from other tables in the book what some of these things are. So here's our spherical harmonics that we'll need from table 4.3 and our radial part from table 4.7. All right, so we'll just plug and chug. We may not have room on this page. So R21 is completely real. I don't see any i's in here, so it's just the square of this. Okay. So we have 1/24, square of this term. We have an a to the -5, square of this, an r squared, and an e to the -r over a. Okay. This piece is R21 squared. Okay, now we'll add in these spherical harmonic parts, and now we'll probably run out of space. So our first one is the 10 spherical harmonic, which is right up here. Okay, So, and it's going to be squared. There's nothing imaginary about this guy either. Our complex is real. So we've got 3 over 4 pi, and again squared, and this is cosine squared. Okay? So there's our first part. Now we'll look at the second part here. I'm going to write it real small down here, and then of course we'll write it again. So 2/3, and now we need the square of y11. All right, here's an I, but it's all up in this exponent. So when we have the conjugate multiplied by just the y11, this part will drop out. We don't even have to worry about it. Okay, and the square also goes away. So we have a plus 3 over 8 pi. If I read that right, 3 over 8 pi sine squared. Okay, so here we go. Here's our probability density, and we're just going to make it look prettier. Some more paper here. Okay, so let's go ahead and start factoring a few things out. I'm going to go ahead and write 1 over 24a to minus 5. I'll write out this r part first. Okay, now what can we factor out? Well, we can, let's see what we have here. So this 2 and this 8 will give us a 4 on the bottom. These 3's are going to divide out, and these 3's are going to divide out. So it looks like both of these parts here have a 1 over 4 pi. And then what's left over is just sine squared plus cosine squared. Or cosine squared plus sine squared if we went in the same order here. All right, and here's our nice trigonometric identity that this equals 1. So our answer, the probability density, if we measure the position of the particle of finding it at r, theta, and phi, is this. We take up 4 times this, so this is a 1 over 96 pi. A to the minus 5 r squared e to the minus r over a, and that's it. Alright, so for part H, if you measured both the z component of the spin and the distance from the origin, these are compatible observables, what is the probability density for finding the particle with spin up and at radius r? So our the radial right, the radial probability density is just given by this part right here, okay? So I'm going to write this probability, we want the spin component on z, so the ms equals positive, right? Spin up, so equals positive 1/2, and at radius r. So the probability of this, all right, so that is just multiplied, we have the probability of finding it at radius r multiplied by the probability of finding it in the spin up state. And again, these are compatible observables, so we don't have to worry about the uncertainty principle or anything weird happening, or like one measurement changing, affecting the results of the other measurement, right? So first, let's, I'm just going to write this out this way. So the probability of both of these is equal to the probability of finding it in the spin 1/2 state multiplied by the probability of finding it at r. I'll write it like this, okay? All right, so what was the probability of finding it in the spin plus the spin up state? That's from this eigenspinner right here. And if we remember, the coefficient squared of this is just 1/3. So if we were to make measurements of our spin up, spin down, we'd get 1/3 spin up and 2/3 spin down for a big ensemble of these particles in this state. So our P1/2 here is equal to 1/3. All right, and the probability for finding it at radius r is just equal to the radial part of the wave function squared. So R21 conjugate R21. Okay, and as we said before, we know this particular radial part here, there's no i's in here, so it's just square. Just your average square. So our answer for finding spin up and at radius r is equal to 1/3, the chance we find it spin up, multiplied by the square of this again. So 1/24 a to the minus 5 r squared and e to the minus r over a. Okay, we can combine these real quick. What is this? 72. I need to go back and learn my multiplication tables. R squared over a to the 5th, e to the minus r over a. So there we have it. This is part H, the answer for this marathon problem. At least some of it was very easy and some of it was a little bit more involved.